Welcome to The Explainer. Today, we are going on a seriously wild ride. We're going to travel from the most abstract, mind-bending physics of the deep cosmos all the way down to that everyday piece of technology you're probably holding in your hand right this very second. So I want you to think about this for a second. What on earth do ancient, massive galaxy clusters have to do with you finding a new restaurant on your phone? I know, it sounds completely bizarre, right? There's no way those things are linked. But stick with me, because by the end of this explainer, you are going to see exactly how these two seemingly unrelated things are actually intimately connected. All right, let's get right into it. Act 1, the fabric of space-time. To really wrap our heads around how the universe works, we actually have to rewind the clock a bit. Specifically, back to November 25th, 1915. That's the exact day Albert Einstein published his groundbreaking field equations, which introduced the world to general relativity. You see, before this, everyone basically thought of gravity as just a pulling force. But Einstein, he showed us something so much stranger and honestly a lot more beautiful. He proved that gravity isn't a pull at all. It's actually the curvature of space-time itself, caused by massive bodies. If you remember your high school physics classes, you probably learned Isaac Newton's version of gravity, right? You drop a ball, you calculate its downward acceleration at 9.8 meters per second squared. And, for everyday stuff here on Earth, Newton's invisible pulling force works perfectly fine. But it completely falls apart when you try to explain the extreme universe. Einstein's gravity threw out the old rulebook. He revealed that space and time aren't separate things at all. They're woven together into this single, flexible structure. Picture it like this. Imagine taking a large piece of stretchy fabric and pulling it tight between a couple of people. Now plunk a heavy softball right in the dead center. It creates a deep dent in the cloth, right? Well, if you roll a smaller ball across that fabric now, it's going to look like it's being magically pulled toward the softball. But it's not. It's just following the natural curve, that dent in the cloth. This is literally exactly how massive objects in space curve the fabric of space-time. NASA actually sums this up perfectly. They say gravity can be thought of as the movements of particles through curved space-time. Everything out there, whether it's a huge planet orbiting a star or just a tiny beam of light shooting through the void, they are all just coasting along those natural, invisible curves created by heavy objects. Which brings us to Act 2, cosmic magnifying glasses. Okay, we're going to zoom way out now, about 4.5 billion light years away from Earth. Out there, we find mind-blowing phenomena like Abell S1063. It's this immensely massive galaxy cluster. And because it's so incredibly heavy, it bends space-time so severely that it acts as a gravitational lens. It literally catches the light from even more distant galaxies hiding way behind it, bends that light around itself, and magnifies them just like a giant glass lens. The James Webb Space Telescope actually uses this exact quirk of general relativity to peer deep into the distant past. Now, what's really wild is the sheer scale of what we can achieve using gravity as our own personal telescope. Take a look at the GLIMPSE observation program. They used 120 hours of total observing time across 9 separate near-infrared wavelengths. And because they tapped into that gravitational lens of Abell S1063, they were able to spot candidates for galaxies that existed a mere 200 million years after the Big Bang. We are literally using Einstein's curved spacetime to look back at the absolute dawn of the universe. All right, let's keep moving. Act 3, surfing the solar system. Let's bring things a bit closer to home, back to our own cosmic backyard. Because NASA doesn't just passively observe gravity, they actively use it to travel through this amazing maneuver called the gravity assist. Here is how it works. First, a spacecraft approaches a massive revolving planet. Second, as it falls toward the planet, it gets pulled right into that planet's massive orbital momentum. Third, it slingshots out on the other side with increased speed and a totally altered direction. Essentially, the spacecraft is stealing a tiny fraction of the planet's momentum to violently propel itself forward. If that's kind of hard to picture, think about it like this. Imagine a kid throwing a tennis ball at 30 miles per hour, straight at the front of a freight train moving at 50 miles per hour. Wham! The train hits the ball and transfers a huge amount of its momentum into it. That ball is going to ricochet off at a blistering 130 miles an hour. That is exactly the kind of massive kinetic exchange happening during a planetary flyby. Except, instead of a physical collision, the spacecraft and the planet are interacting through the invisible grip of gravity. And this isn't just a neat trick, by the way. It's been an absolute lifesaver for some of our most historic missions. Voyager 2 used Jupiter, Saturn, and Uranus to reach the outer edge of the solar system. Galileo used Venus and Earth just to make it to Jupiter. Cassini bounced around between Venus, Earth, and Jupiter to build up the momentum it needed to finally reach Saturn. Without stealing this momentum via gravity, our rockets simply couldn't have ever carried enough heavy fuel to reach their targets. It just wouldn't work. And that leads us perfectly into Act 4, Relativity in your pocket. So remember that weird question I asked at the very beginning? The one connecting ancient galaxy clusters and your smartphone? Well, it's finally time to connect the dots. Whenever you open up a navigation app to find a restaurant or get directions, you are tapping directly into the GPS network. This whole system relies on a constellation of satellites orbiting roughly 20,000 kilometers above the Earth. To pinpoint your exact location down here on the street, those satellites have to calculate timing precision down to billionths of a second. But here is the kicker. Without taking relativity into account, that accuracy degrades instantly. Right above our heads, there is this literal cosmic tug-of-war going on. First up, we have Einstein's special relativity. Because the GPS satellites are moving so incredibly fast, their clocks actually run about 7 microseconds slower per day compared to our clocks on Earth. But, and here's the twist, acting exactly opposed to that, we have general relativity. Because those satellites are 20,000 kilometers up in the sky, they experience slightly weaker gravity than we do on the ground. That stretches space-time differently, which actually makes their clocks run 45 microseconds faster per day. So the crucial point here is the net difference, 38 microseconds. Because of the combined effects of special and general relativity pulling in opposite directions, the clocks on the GPS satellites tick faster by exactly 38 microseconds every single day. I mean, that sounds like a completely meaningless, microscopic amount of time, doesn't it? But get this. Engineers just ignored Einstein's equations. If they didn't mathematically correct for those tiny 38 microseconds, your navigation app's errors would accumulate by a massive 10 kilometers every single day. No joke. That new restaurant you're trying to find, your phone would tell you it's across town or maybe even in the next city over. You are literally holding a device right now that relies on the curvature of space-time to function properly. It's kind of beautiful when you think about it. From peering at the very dawn of the universe through galaxy clusters to stealing momentum from Jupiter, all the way to guiding your daily commute to work, it is all connected by the exact same brilliant mathematics. Gravity shapes the entire universe, but what invisible forces are shaping yours? Thank you so much for joining me for this explainer. Keep wondering, keep learning, and as always, stay curious.